Welcome to PowerUP, a podcast show hosted by Maurizio Di Paolo Emilio that brings life to some of the stories on power electronics technologies and products featured on powerelectronicsnews.com and through other AspenCore media publications. In this show, you'll hear both engineers and executives discuss news, challenges, and opportunities for power electronics in markets such as automotive, industrial, and consumer. Here is your host, Editor-in-Chief of Power Electronics News and Embedded.com, Maurizio Di Paolo Emilio.
Hello everyone, and welcome to this new episode of PowerUp. Today we will discuss the technologies that would shape the future of semiconductors. The title of this episode is Unlocking Semiconductor Efficiency with MST Technology. So we are exploring Mears Silicon Technology, MST, Atomera's innovative solution for improving the performance and efficiency of silicon-based devices. MST has the potential to transform power electronics, telecommunications, and advanced computing by enhancing mobility, reducing leakage, and boosting reliability, all while being compatible with existing manufacturing techniques. Our guest is Shawn Thomas, Head of Advanced Logic Nodes and Power Business at Atomera, and we will discuss how MST is enabling new possibilities in semiconductor design and manufacturing. Hi, Shawn. Thanks a lot for being here. How is it going?
Very well. Thank you, Maurizio. Thanks for your time.
Thank you. So where are you located now?
We're located right now in California in our offices in Los Gatos.
Good. So today we will talk about MST technology, as I said at the introduction, at the beginning of this podcast. But before that, tell us more about you. Please introduce yourself, your role at Atomera, and Atomera, of course, as well.
Sounds good. Thank you. Yeah, so a little bit about myself. Obviously, I'm Shawn Thomas. I joined Atomera earlier this year as my role at Atomera is responsibility for business development for our technology, and working with customers on engagements of being able to penetrate and get MST, which is one of our core technologies, adopted in various device architectures. So, my background, I have a background in epitaxy, silicon-based epitaxy, doing it for about a couple decades or more. But I've had experience at companies across the semiconductor chain. Starting most recently, I was at Applied Materials in their epitaxy business unit, responsible for a lot of their epitaxy process development for advanced logic technologies, so 2 nanometer and beyond technologies. Also responsible for kind of evaluating some of the new products that the company is trying to roll out to customers to enable these advanced processes. Prior to that, I was with Global Wafers, a substrate manufacturer, wafer manufacturer. My last role there was responsible for SOI development. So our team did the advanced SOI development for both 200 millimeter and 300 millimeter. So focusing on RF technologies as well as FDSOI type technologies at both wafer diameters. And prior to that, I was with ASM, also in their epitaxy business unit, similar role to what I was doing at Applied Materials. And prior to that, I started my career as a young engineer working at Motorola, doing a lot of device and integration. I was able to work on a broad array of technologies, from RF to photonics. It was a good experience, good foundation.
Good, great. So today we are going to explore Mears Silicon Technology, MST, of Atomera. So has been promoted as a great innovation in the semiconductor industry, offering benefits in different ways. So can you explain what MST technology is and how it improves silicon-based devices?
Sure, very good. Yes, let me start with what it is. So MST at the most basic is and it's an epitaxial process in which we insert oxygen into the epitaxy film. So traditionally, when you're thinking about epitaxy, you don't think of oxygen as something you want in a film. We tend to think of it normally as something you want to avoid in silicon epitaxy. But in our technology, we put it in a controlled way such that we're still able to control the epitaxy and still maintain good quality of the epitaxy. So you're putting in these atoms of oxygen in specific layers of the epitaxy, and that has a then benefit when it comes to a device. And in terms of, and the benefit depends upon the type of device you put it in. So, fundamentally, one of the main advantages of MST and that inserted oxygen is it can control diffusion, dopant diffusion, both N-type diffusion and P-type diffusion. Typically, the P-type dopants are boron. N-type dopants are typically phosphorus and arsenic. And so, by being able to control diffusion, it becomes really important as device technologies have scaled, because now as you go from originally, let's call it microns of gate length down to 2 nanometers, you don't have that much margin to be able to allow dopants to diffuse and still have transistors retain their ideal performance. So, we try to use MST as a way to kind of control and engineer doping profiles to optimize device performance. And the way we do it, again, I said, depends on the device architecture that you're looking at. So, in the case of, I'll say, advanced logic transistors, it has actually kind of 2 benefits that are related to each other. If you add MST, I'll call it next to the source drain region between the channel tip and the source drain itself. That way, you can actually control the amount of diffusion that occurs into the channel. So that has many device benefits with respect to Dibble, and you can also actually engineer your source drain to reduce resistances as well. Obviously, another key parametric for transistors these days, because a lot of the performance is kind of lost in the extrinsics of the device rather than the intrinsic performance of a transistor. The other benefit that we can think about for particularly these ultra small gate length devices, fundamentally in gate all around, you want to have an intrinsic channel. But when you go through the process flow of transistor fabrication, you will still get dopants that kind of diffuse into the channel, and then you'll have random dopant fluctuations in the channel, which can affect the current in the transistor. So with MST, and so why is that important? That leads to a lot of variability transistor to transistor, because the diffusion amount may be different transistor to transistor. Now, if you add MST in between the channel edge and the source drain, and you're able to block that diffusion, you can reduce that dopant fluctuation and improve your variability transistor to transistor. So, that then translates to things like yields, more consistent circuit performance. So we find that there's intrinsic kind of device benefits that translate up to overall performance benefits for circuits and manufacturing yield.
So one of the main key, one focus, talking about epitaxial layering process in MST. So this is central to MST benefits. So enhancing different properties, critical properties like mobility and leakage, reducing leakage. So how does this process work? So why is it so effective?
Yes. So for MST, when we talk about improving mobility, again, there's a couple ways that we've looked at how this can improve mobility. When we incorporate, we've done some experiments in collaboration with universities, specifically Professor Subandata, in which we've put MST in the channel or below the gate dielectric interface. Below the high K metal gate, which is the typical gate stack that you see in advanced transistors. And one of the things that we observed is the oxygen from the MST and interacts with what's called the IL layer of the gate stack. So the IL layer is a kind of a poor oxide that's below the actual high K dielectric. And we get oxygen exchange between the IL layer and the MST layer. So you're having we'll call it a higher quality oxygen from the MST that is kind of exchanging places with the quote unquote poor quality oxygen from the IL layer. And we've seen that helps to improve the quality of that IL layer and reduce the Coulombic scattering at that interface. So in that way, we're able to improve the mobility of a transistor. So from a leakage perspective, from a I'll call it advanced logic type transistor, it's not so much leakage per se. The leakage benefits we see are maybe different types of transistors. For example, things like power devices or RF-SOI devices, where you're trying to engineer the doping profile at the in certain regions. Let's say, for example, in power, you can confine carriers, your channel, to a certain region. Let's call it near the field plate area, and you reduce the amount of carrier leakage that flows to the substrate. So by the MST can block that carriers from going down to the substrate and contributing to leakage current. Right? So that's another way that we look at being able to engineer the profiles for the transistor to reduce leakage.
So talking about devices applications, so MST has shown potential across different applications, so from power electronics to advanced computing. So what types of devices industry can benefit the most from this technology?
Yeah, so there's a few areas that we're focusing on. We know one of the areas that we're really excited about is in power electronics, and we can talk about power electronics from multiple perspectives. But let's specifically talk about silicon for a minute.
Sure.
A lot of we have a number of different architectures that we've put together, and we call them MST SPX, and what that is basically trying to modify typical LDMOS type transistors to be able to achieve higher breakdown voltages. And higher breakdown voltages means above 48 volts, and we're getting pushed by customers to try to go above 50, 60, 70 volts in silicon. And why is that important? If you look at the power electronics today, one of the big opportunities driven by our massive demand for communication, whether it's AI or just raw video, is data servers. So, data servers consume huge amounts of power. And there's an industry trend already to move from 12-volt supply to a 48-volt supply to be able to reduce that net power by about 16x. So we envision that our MST technology can be used to help enable transistors to push that breakdown voltage to be able to support a 48-volt application directly on die. And in that case, that's contributing to being able to meet the needs of data centers to reduce that power consumption, the power hungriness of that center.
So a benefit and a major advantage of MST is its seamless integration into existing manufacturing processes. So can you tell us more a bit? Can you elaborate on how it achieves this compatibility without disrupting the workflow of the production?
Yes, great question. So if you look at various applications, and it'll be whether it's advanced logic or power electronics or RF. Increasingly as technologies advanced, the epitaxy itself has been used more and more as a tool to help engineer device performance. And for example, in logic transistors, we've had silicon germanium epitaxy introduced in source trains back at 90 nanometer type technologies. So it's been here for many decades, or Yeah, well, going on a couple decades. But so because epitaxy is now I call it accepted tool that is in the process flow, MST can be inserted because it's not adding an additional cost. You're already doing epitaxy, and we're just adding I'll call it a process step within an existing epitaxy step. So, for example, again, I'll pick on logic again, but in a logic transistor, you're going to do source drain epitaxy. For P channel, you'll do silicon germanium boron. For N channel, you'll do silicon phosphorus. So you're putting that epitaxy in the source drain region. So MST is just going to say, okay, right before you start your silicon germanium or your silicon phosphorus epitaxy, we'll just add a little epitaxy step of MST in there. So you're just adding a few steps to a few, I'll call it process steps within a recipe of an existing process module. So it's really not adding too much more a burden on or cost to a flow, right? You're adding, you're already doing an epitaxy step. So we try to leverage that, try to make it as seamless as possible. There are other applications, where, for example, I can think of RF-SOI in some specific applications that we're looking at that, it may not be the standard, where we insert MST may not be standard. So it may be adding a process step, but there's still epitaxy, call it further on in the flow. So the tool itself is not something you have to buy specifically for MST, just you're adding that MST step. But what we end up seeing is by adding this MST step, we can also offset that cost by reducing or eliminating other steps. So, for example, we can minimize some implants or reduce some cleans that are made unnecessary as a result of doing the MST step. So, we look at trying to make sure that the ability to add MST to a flow is not a dramatic cost adder to an existing flow, because we know that's also one of the barriers of entry for customers to adopt it. Right, epitaxy, is one of those, I'll call it more expensive process modules in a process flow. So people, when they adopt it, they don't adopt it lightly, and it's for a specific need, and it's a necessity. So we want to make sure that we're leveraging existing, epitaxy steps and helping to engineer those profiles.
Great. So very interesting technology. So MST is gaining attention for its scalability and for the potential across different industries that you mentioned. So just in conclusion, Shawn, my last question. So what's next for Atomera? So in terms of next advancements for adoption, MST adoption, and expanding, of course, application industry. So we will see more applications for sure.
Yes. Thank you. Yes, we are. I've talked a little bit, mostly about the applications of MST in traditional silicon devices, whether I spent about logic transistors or RF or memory, but we've been now expanding MST into compound semis. So more specifically in the area of gallium nitride. So, gallium nitride has been another hot area over the last number of years for power electronics as well. And what we've done and we've shown with initial experiments is that we've been able to apply MST to a gallium nitride on silicon process to improve the overall quality of the gallium nitride that's grown on silicon. So where we do this is we actually put MST at the starting substrate layer, at the silicon level, not inside the gallium nitride, but at the starting silicon substrate. We put our MST layer there. And you can grow your traditional gallium nitride structure on top of that, which typically includes the buffer layers to manage strain, as well as the active gallium nitride on top. And what we found is that we've been able to show an improvement in the bow and warp of the wafer, and as well as the crystalline quality or the defectivity due to dislocations in that gallium film. So we're excited about that because again, gallium nitride is getting a lot of attention in the area of power electronics and electrification, and we think that this is going to be an enabler to be able to achieve better, higher quality gallium nitride, which can enable gallium nitride to maybe scale up to more. It'll help gallium nitride as it scales up to 300 millimeter. A number of people have already talked about and now it's doing 300 millimeter GaN on silicon. So we're excited about that and the opportunity to improve that overall quality and hence the device performances as well.
Yeah, good opportunity for electrification, as you said.
Yes.
Okay, Shawn, thanks a lot. Thank you for your time. Thanks for joining us at the PowerUP podcast. Thank you.
Hey, thank you, Maurizio. Nice talking with you.
That brings us to the end of this episode. Stay tuned for more news and technical aspects about power electronics. If you are listening to this on the podcast page at eetimes.com or powerelectronicsnews.com, links to articles on topics we have discussed are shown on this page. Power Up is brought to you by Aspen Core Media. The host is Maurizio Di Paolo Emilio and the producer is James Eade.